for Stokes-Helmert, they do like that. They have two spaces. The real space, and they have Helmert space. So what is happening here? If we have this topographic, and we have the geoid here, and we have this topography, and we have the geoid here. We have atmospheric masses. Atmosphere in both. And we have topography. And we write topo in both of them. Then they have the gravity anomaly here. The gravity anomaly data. They remove the effect of atmosphere and the topography from the data. Then they go to a no topography, no atmosphere space, which is called Helmert space. And they have the data G, no topography, no atmosphere. And here they perform downward continuation. And they come to something which is similar to geoid, but it is called geoid. When they do this, they continue. Later, they will apply the indirect effect. To change the code geoid to this way. If I write mathematically this method, we will have, okay, geoid r over 4 pi gamma integral. They modify the kernel. Delta G, it is minus delta G, no topography, no atmosphere, downward continued, plus, now the effect of this truncation of the integral modified, if it comes in, it will be plus r 2 gamma, so 2 to L, it will be Rn, delta Gn, which is come from EGM, plus then no topography, geoid, no atmosphere. And the downward continuation here is done by DWC, downward continuation by inverse solution of Poisson integral. So they numerically solve this integral number for doing the downward continuation. So they perform the downward continuation with the spirit, and also they remove the long wave structure and they restore it here. So you see that they also use a satellite-only model to remove the effect of long wavelength structure. They will remove the effect of topography and atmosphere, of course, with a compensation mechanism, because I already explained that this effect, if especially topography is larger than gravity, we need a compensation mechanism to make it smaller in the order of gravity, to make the data a little bit smooth. And thereafter, we perform the integration. They perform the downward continuation of the result, and they will restore again these removed effects to the computed geoid model. So It is also a form of, you see that the form of remover compute restore also is applied here. And again, the problem with the gravity anomaly and the best choice of the gravity model for removing the line wave obstruction is here as well. And the problem with downward continuation with integrals also is not easy, because when the data are dense, these integrals will be very difficult to solve. So I can explain what they do here actually. They have a gravity anomaly at the surface of the Earth, for example, and they want the gravity down at the geoid level. Then we solve this integral. They have a kernel which connects these points to down here, a point, and they have gravity and downward continuation. They will write an equation for that. This is a summation I up to the number of the grids. How large is the grid here? The grid of the data. So it's a limiting factor. For example, if you want to determine the gravity anomaly at the surface of the geoid over Ethiopia, you cannot perform this downward continuation all over the area. You have to divide your country to small pieces and perform piece by piece downward continuation. And normally up 3 degrees, or maybe small 3 degrees, or maybe smaller. So it's about number of the gravity anomalies, and you will write a linear combination of this data and your kernel. So for each gravity data at the surface of the Earth, you can write an observation equation like this. And for each small portion, for example, you have 100 gravity anomalies here, and you need to have at least 100 gravity anomaly above this area. And when you write for the first one, you write the equation for the first one and all the gravity data down there. And for the second data, you will write it. And after a while, you will have redundancy, and you can solve it by this squares approach. This type of integrals this method is called integral inversion, and it's very sensitive to the error of the data and very hard to solve it. And you have to apply regularization to get a stable solution. At the end, when you determine this data, the error of the data, the recovered data over this marginal area, will be much larger. Then you have to truncate them and remove them. Again, it's called truncation error, or it's either spatial truncation error. Probably you have heard about Gibbs effect. It's very similar to Gibbs effect. So this problem is not that easy to solve, especially for a country, and if you have a very dense data. And also gravity anomaly is not very small function.